Hello there, welcome back to our channel. And this time, as you can see on the screen, we are given a small signal model of a BJT circuit. And we have to derive a circuit diagram from this given small signal model. So as I have written here, this is basically an equivalent circuit for a voltage divider bias of a BJT. It is also called as equivalent circuit. Usually, it is the practice that we are given a BJT circuit, whether a fixed bias circuit, collector to base bias circuit, or a voltage divider bias circuit. These three kind of biasing we have seen for NPN BJT or PNP BJT in our previous module. So if you are new to this module, please refer back to those modules. So after we are given a circuit, as I said, we basically derive its small signal equivalent models such as this to understand the behavior of that circuit in terms of its DC response or AC response. Now here is the reverse situation. We are given this equivalent model, and now I am going to derive an actual circuit of which the model is. So before that, I want to understand all the components that is placed inside this model, and I want to understand what this circuit could be. So let us start one by one. This is an input side of the circuit. This is an output side of the circuit. So this is essentially a two-port hybrid model of a BJT. Okay. And furthermore, I want to understand here is the input signal Vi that I'm going to apply across the input port. And because of that, the input current II will start flowing into the circuit. At the output side, I'm measuring the output voltage, obviously. So now you carefully see this is the base pin as noted. This is the collector pin is as noted, and this is an emitter pin as noted. The resistance between the base and the emitter is modeled by R pi. This is basically a base emitter resistance of the BJT across which a voltage drop VBE, that is the voltage across base and emitter, is generated. And when the BJT gets into the conduction, I have a collector current that is modeled by this dependent current source, which has a value of Gm times VBE. So IC is Gm times VBE. This current is flowing through an output transistor of the BJT, which is basically the ratio of VCE divided by IC when VBE is equal to 0. Now there is an input current that is getting split into the two parts. One is the current that is flowing through this equivalent input resistance R dash, we will see. And then the another component of this current is the base current, that is IB. I have explained to you this is an IC, which is Gm times VBE. Then there is a current that flows through the resistor RE. This is called as emitter degeneration resistance, which we have seen in the BJT circuit, and the value of it is given by IC is equal to IC plus IB, where IC is beta times IB. Okay, if you spread this equation further, then IE can be written as beta times IB plus IB. Okay, so, and this is a load connected to the collector terminal of the BJT. When you look at the impedance of the network from the input side, that is called as input impedance, ZI. When you look at the impedance from the output side of the circuit, that is called as ZO, which is VO over IO. This is an output current. And ZI is VI over II. Here it is. There is an impedance noted here. If you look at the base and emitter pin of the transistor, that impedance is called as ZB. So this, okay. Is there anything left? No. So now I have understood all the components and the devices, the pins and the currents and the voltages and the impedances on this circuit. Let me draw the circuit diagram for this and I will explain. So basically I will start with drawing a BJT symbol. This is assuming this is the model of NPN transistor where I am having this kind of arrangement. So here is my base pin. Here is a collector pin and here is an emitter pin of the BJT. Now I have this from collector pin to the VCC. Let's say I have this RC connected. Now to the base pin, actually, I am having a resistance divider network that will help me to set up the bias for the BJT to be used it for a specific application. I will call that resistors network is R1 and R2. Then there is this emitter resistance RE, and here my circuit is connected to the ground. Okay. Now RC is there, RE is there. I have model R1 and R2. And now there is, I haven't shown the capacitances into the equivalent model, so I neglect that. And here I have an input signal VI actually that I am applying. This is my VI. And then I have the output that I am measuring for the circuit. So here will be, let's say, the output. Okay. So what I'm doing here is that when I apply the VI, I have the input current II, which is flowing into the circuit. Now this R dash is modeled as a parallel combination of R1 and R2. And that is what I have shown here. This is the resistance between base and the ground. From the base and the ground, I can model this resistance, the equivalent circuit. So when I draw the small signal model, actually I have to get this VCC is equal to 0. It means I have to connect this terminal with respect to ground while doing the small signal analysis. And when I do that, because then this is an AC source and this is connected to an AC ground actually. Okay. And then I make the model like this. So when RC is connected now between the collector and the ground, that is what I have seen. RC is connected to the collector and the ground pin. One end of the R1 is connected to the ground because VCC is grounded now, and one end of the R2 is connected to the ground here also. Okay, that's why I have modeled this R dash to be the pin between the base, here is my base, and with respect to ground. So that's a parallel combination of. What about the RE? So look at this. RE is basically connected between emitter and the ground. That's what I have, what it is here. And I have modeled that. And the current flowing through that is IE is IC plus IB. Okay, it can also be written as IB beta plus 1 multiplied by IB, where IB times beta plus IB after expanding this equation. Now, the collector current that is flowing from collector emitter is modeled by this GM times VE, and I have this resistance RO. This is an output resistance of the BJT, which is basically VCE times IC at PBE is equal to 0. Okay, and actually this is an output resistance of this transistor. Okay, and the GM times VBE is the collector current. So this is how we actually have got this equivalent circuit and its actual circuit. So if you are given a circuit like this, you can get back to derive its equivalent circuit like this. And if you are given this equivalent circuit, you can actually model and understand that. Now, what is the input impedance of the circuit? So if we look at from this side, ZI, it would be VI divided by II. Look at this, II is getting split between the two parts, that is the IB and the current that is will flow through the parallel combination of this network, R1 and R2. Okay, so I think I have explained to you all these things. Now, what is the output current? If you want to get an output current, so you basically do one thing, you apply a test signal V output and then get the value of I output, and that will be your ZO, that is the ratio of voltage over the current, output voltage divided by input voltage, output current. So I think that's it. We have derived the equivalent circuit, and from that we have derived the model or vice versa. So hope you found this video useful. If you did so, you can like and subscribe to our channel. Here I forgot to one thing, that you can actually see that you can then from this equivalent model you can derive many things. For example, take the derive the expression for the gain, that is the voltage gain, which is the ratio of output voltage divided by input voltage. Okay, so right there you can do that. Okay.